Could you really have no life? No, I'm just kidding. I'm kidding. You just want to learn about rockets. Okay, so ion propulsion systems, these are very cool. These are electric rockets. They are electrically powered rockets. And the cool thing about them is that they generate enormous exhaust velocities. The rocket that powers the Dawn probe has an exhaust velocity of 35,000 meters per second, right? Saturn V is something like in the thousands of meters per second. A little Estes rocket is something like 700 meters per second, right? So these are generally the alpha rockets. And the way they work is actually quite simple. You get an ion, and the ions they use for this thing is xenon because it's so darn heavy. Look where it is in the periodic table, right? It's a noble gas. It's not going to react with things. You ionize it by taking an electron off it, and then you put it here, and you make this side positive and this side negative. And of course, a positive charge will be repelled by that and attracted to this, so it'll go flying this way, right? And it'll reach 35,000 meters per second, right? In this little space here, right? Then the negative electrode here has holes in it, so it goes flying on through. It's like, oops, right? And then when it flies past here, right, if you look behind you, you've got negative and positive, so there's no net force, right? But here's the problem, right, is that you can't be always losing negative charge or positive charge, right? That means that the spacecraft is going to build up a tremendous negative charge, right? So the electrons that they take off of these things to ionize them, out here they put them back on. This is just, they're showing a wire here, okay? But that's what you do, just heat up a metal wire, and that would actually, metal wires have lots of electrons, and they would spray those electrons back onto these things as they go by, and they go, here's your electron back, you know? Otherwise, these things would they'd get such a tremendous negative charge on your spaceship that these things would come back and your thrust would be negated. Okay, here's a diagram of this. Here's a picture of the Dawn spacecraft. Where does the power come from? Well, it's a solar rocket. What could be more, cool than that, right? NASA actually is thinking of having things like this be like tugboats to pull things up toward the moon, like to build, instead of using chemical boosters, use solar-powered rockets to slowly, over the space of like 2 years, lift things up. So that's kind of a cool thing. Here's a better diagram. There's the ion beam. Here we're injecting electrons to neutralize the beam. And then electrons impact atoms to create ions. I didn't know that. Look at that. That's cool. Okay, so it's a gridded xenon ion drive. Okay, and there probably is a way to get even a bigger change in velocity, because this is basically a particle accelerator. And then you really have no life if you go and do these calculations here, right? Okay, so here's the Dawn. There's its mass, right? It's got this exhaust velocity. And then here's the crazy thing about these rockets is that they generate a thrust. The entire thrust of this engine is equal to the weight of a sheet of copier paper. Okay, that's it. But in space, there's no gravity, there's no air friction, right? So that force is going to cause an acceleration, a very slow one, but it can burn for an exceedingly long amount of time, right? So here's why, right? Let's figure out the burn rate, right? Force times time, mass delta V, right? Okay, 0.092 times 1 second, right? That's what you do to find the mass burn rate, is the mass you burned in that 1 second, right? Times 35, in this case, freaking 1,000 meters per second, right? So the answer is 0.092 divided by 35,000. And you get 2.62857 times 10 to the minus 6th kilograms per second, right? Okay, that is, what, 2.6 milligrams of fuel every second, right? Fuel's going to last a long time, okay? And then this is the big thing, right? What is the change in velocity, right? This is called delta V, right? And that's the cool thing about these ion drives, is that they can give a spacecraft an enormous delta V, much more than like a chemical rocket can. And I'm going to cheat. I mean, I could do, force times time, like that force, right? And then figure out how long it takes to burn 50 kilograms of fuel at this rate. And that would just simply be 50 divided by that and get the time, right? Equals the mass, the average mass of the spacecraft times delta V. And this is an approximate calculation. because in reality we have to use calculus. The acceleration is getting more and more and more and all this stuff, right? But let me show you a simpler way to do this. I'm going to say that the spacecraft's change in momentum is equal to the change in momentum of the fuel, right? So if 50 kilograms of fuel undergo a change in velocity of 35,000 meters per second, and this is not an exact calculation, the spacecraft has an average mass of about 745 during that time, right? And then there's its delta V. And if you go 50 times 35,000 divided by 745, you get, and again, this is, if you need calculus really to do this, 2348.99, but this way is, as good as any non-calculus way of doing it, right? Which is about what I got there, right? Okay. Hey, thank you for being mindful of gridded ion propulsion systems.